Welcome to Differential Equations, Chapter 3, Section 5. In this section, we'll be discussing repeated roots and reduction of order. So the general format for Section 1 and Section 4 is the same for Section 5. So we have ay double prime plus by prime plus cy is equal to 0. So we're dealing with homogeneous functions once again. So in this case, we're actually going to have b squared minus 4ac is equal to 0. This is actually the part that's underneath the radical in the quadratic formula. So what happens is we'll actually have, so normally we type in something like, well, we have lambda a lambda squared plus b lambda plus c is equal to 0. Normally we'll have it some number plus or minus some square root over another number. So when this is not negative, not positive, only when it's 0, we're just going to get this one number twice. So the general format for the solution of this is actually going to be y is equal to e to the lambda t plus t e to the lambda t. So let's go ahead and do an example here. So from the Boyce DiPrima textbook, we have y double prime plus 4y prime plus 4y is equal to 0. So I'll go ahead and write out all of the quadratic formula. Okay, and let's plug in some numbers. So we have lambda, or we'll just do lambda squared plus 4 lambda plus 4 is equal to 0. So using the quadratic formula, we have negative b, so negative 4 plus or minus the square root of b squared, which is 16, minus 4ac, so minus 4 times 1 minus 16, all over 2a, a is 1, so 2, so it is just going to be negative 2. So we have one solution. Remember, quadratics typically have two. When it has one solution, it's just the same one twice. So now that we have what lambda equals, we can say y is equal to, and then we're going to have the constant, so c1 e to the negative 2t, and then we're going to have the constant, the second one, we're going to add a t, and then e to the negative 2t. And then this would be our general solution for the given problem. So y double prime plus 4y prime plus 4y is equal to 0. If we were given initial conditions, we can solve for both c1 and c2. So with the next problem we have, we are actually given the initial conditions. So we have y double prime plus, minus y prime plus 1/4 y is equal to 0. We are also given y of 0 is equal to 2, and y prime of 0 is equal to 1/3. So once again, we can do lambda squared, lambda squared minus lambda plus 1/4 is equal to 0. We can use the quadratic equation again. I'll go and write it out. So we're going to have lambda is equal to negative b, so 1 plus or minus square root b squared, which is 1, minus 4ac, which is also 1, all over 2a, which means 2, so it is equal to 1/2. So we have this general format, so y is equal to c1 e to the t over 2 plus t, don't forget the constant, c2 t e to the t over 2. And I'll go and write down the initial conditions again, just so you guys can see it. Y prime of 0 is 1/3. So when t is 0, y is 2. So we'll have c1 plus c2. We'll take the derivative of this function, which is going to be y prime is equal to c1 over 2 e to the t over 2 plus, and then don't forget product rule, so we'll do c2 over 2 t e to the t over 2 plus derivative of the t, so we're going to get c2 e to the t over 2. And now we got to plug in 0 for t, and that is 1/3. So when plug in 0 for t, we get c1 over 2 plus c2, because this goes to 0, so just c2. And we'll go ahead and move the 1 down here, so we have 2 is equal to c1 plus c2. We'll go ahead and subtract these two, so 1/3 minus 2 is going to be negative 5 over 3, and then these c2's will cancel, and we'll get negative 1/2 c1. c1, we'll multiply that by 2, we'll get 10 over 3. We can move this back in to the one up top there, so we'll have 2 is equal to c1, so 10 over 3 plus c2. So this is actually going to be 3 1/3, so we're going to get c2 is equal to negative 4 over 3. So we can go back to our general solution right there, and we can plug it in. So we're going to have y is equal to, and we've got c1, which is 10 over 3, e to the t over 2, plus c2, which is negative 4/3, and then don't forget the t, e to the t over 2. And that is our specific solution with the initial conditions.